And the video we're watching is going to be called Warriors of the Net, that will watch over data packets, firewalls, and network traffic is what it's comprised of. And as always, we also have your research, or not your research paper, your review questions, and your quiz due this week as well for Chapter 2. So, again, OSI model we're going over tonight, and the standards that are in networking. There are business standards, governmental standards, not a lot of, not as fun as the game we played just a second ago, but they are something that we need to know about in networking, as far as who makes all the rules for, like, Wi-Fi, wired networks. When a business wants to create something for a network device, they have to go through these organizations that we'll talk about. And then we'll end on the OSI model, what that's all about. So, network standards basically is, as you can imagine, just an agreement, a technical specification that stipulates a product design or performance. An example would be like a standard for a Windows 10 computer. You'll see when you install Windows 10 software operating system, it'll say, here's some standards for you on what you need for Windows 10 to run correctly. Minimal standards, like say you need at least 4 gigs of RAM. Yes.
I lost internet connections.
You did? That's okay. Were you able to submit your name?
No.
Okay, it'll come back. It's been doing that. So just try it periodically. I did restart everything, but it's still doing it. So I'm guessing it has to do with our RVC network. So we are connected to that somewhere down the pike. So, but yeah, it's been happening across campus. So I thought we could just restart the PIX router would fix it, and I think it didn't. So just retry later and you should be all right. So anyway, getting back to the Windows 10, if it has minimal requirements on the Windows 10 operating system install, like how much memory minimum you need, how much hard drive space minimum you need, all that good stuff. Those standards are actually written not so much by Microsoft. They are part of the group that helps write the standards, but they are not the only one that helps write the standards for even their own products. And so we're going to talk about some of those organizations that write those standards, and there are people, guys and gals both, that make a living writing standards, believe it or not. That's all they do. So if you're a person that loves rules, you love numbers and data and making people's life miserable, no, just kidding. No, you love writing standards. Not for everybody. I have a few folks I know that do write standards, the nicest people in the world to meet, and very detail oriented, and so they do a good job. They love being in meetings all the time, and so if you like that, which some people do, you might think about joining boards. You'll hear about some of the boards you can join tonight. Some of the memberships you can join as a member, and eventually work your way up the ladder to be an administrator or administration of those groups. So standards are essentially, in the network world, covering hardware and software. And so it ensures that everything works together. All the hardware, like all the Wi-Fi routers, that they all work together, regardless who buys them and what type of computer they have, they'll be able to use that Wi-Fi router. So in order for everybody to be able to use the devices that are created, there has to be some standards that all these companies have to agree upon, that they're going to make a Wi-Fi router with the A through Z standards, basically, all right? And they're going to hit the minimum standards, most of them, and they get a little sticker on them saying you have been approved with this standard, which you'll find out some of those tonight, what those are. Standards, again, are a minimal acceptance performance. It's not ideal performance. It's not maximum performance. It's low-level, minimal standards. Like on a Windows Server operating system, the Microsoft Server minimal standard is still around 8 to 12 gigs memory, which is very, very low memory for a server. But again, it's minimal standards. And even for PC users and Mac users, the OS itself, if you read the standards for that, the minimum standards are pretty low. You've probably seen those. The bar set pretty low on purpose. So many organizations oversee different organizations, different industry standards. One of the bigger ones that we'll talk about is ANSI and IEEE. These folks set the wireless standards. So everything we hear and touch and can configure in the Wi-Fi world is done through these organizations, ANSI and IEEE. And it's a network professional's responsibility to kind of know these standards and understand the critical aspects of how it's required to meet those standards within your network. So ANSI is 1,000+ representatives. It stands for American National Standards Institute, both from industry and government. So it's a quasi governmental industry both. Determines standards for electronics industry and other fields. It requests voluntary compliance from all the companies that make hardware like Wi-Fi routers. Obtaining an ANSI approval is pretty rigorous testing it goes through from both the technical and non-technical folks. The technical go over, as you can imagine, the device, how it works, how it functions. The non-technical governmental folks go over the things like what type of liability do we have? Does it meet the FCC standards of where it flies in the air? All that stuff they're going to look at. ANSI standards are online. They're called white papers, and they can be in the thousands of pages, all of their standards. So anytime if you have nothing to do on the weekend, you can Google ANSI white papers and just read one of their theoretical papers on Wi-Fi standards. And I know you won't do that, but anyway, tongue in cheek. EIA and TIA, Electronic Industries Alliance. When we do the cabling lab, you'll actually see the names of these acronym names on the wires. If you were to reach down and unplug your wire on your computer now, the Cat5 wire, you would see these names stamped on the cable itself. And it's a trade organization from the U.S. electronic manufacturing firms. They set standards for members, help write ANSI standards, and they also lobby for computer electronics industry legislation. TIA, the telecommunications industry, formed in '88. EIA is a subgroup of the former U.S. Telecommunication Association, USTSA. The focus of TIA is information, wireless, information technology, wireless, satellite, fiber optics, and telephone equipment. TIA, EIA 568B series, that's important to note because that's what our cabling is on. That's all of our Cat5 cabling is on that series, B and A both. And so when you see, you'll actually see that in full on multiple times on a wire, a Cat5 wire, and you'll see that when we do the lab. It's guidelines basically for network cabling, so the wire quality, the sheathing quality, the strength of the cable, all of that material of the cable is all met through the standards TIA, EIA 568B series. Guidelines for installing cable network in commercial buildings. Not home buildings, or not your home residential, but that's really about the only cabling that most people use in home is this right here. When you go to any store to buy cabling, it's going to be this standard, is going to be stamped on it. Tektronix here in town, by the way, if you want to buy a bulk cable, like 1,000 feet, like after we do our lab, you're like, hey, I want to do this for fun. I want to see how good I can get at it. I want to do this for a living maybe. There's people that do it for a living, by the way. That just run cable and install cable, and that's all they do. They make pretty good money. But Tektronix downtown is a pretty good company that you can buy 1,000 feet at a pretty decent rate, like $50, $75. And you'll learn about all that and the tools involved and how that works. IEEE, Institute of Electronics Engineers. It's an international engineering society. They do meet, by the way, here on campus a couple times a semester. They got a good student chapter, which we'll talk about in a second. I do recommend getting involved with the student chapter of IEEE. It does cost a little bit, but it's well worth it. You get, monthly magazine, online resources, training. They have conferences you can go to here in Illinois. I think the one big one they have is down at McCormick once or twice a year. No, it's once a year now, where you go in and you have these training sessions where it's kind of like the game we just did. You learn something, and then right after you learn something, you have a challenge in groups, and you kind of, apply what you just learned. And it could be on ethical hacking. It could be on how fast you can set up a network. It could be on how fast you can subnet a network, whatever networking they choose to do. And so the goal of the IEEE is development and education in electronical engineering and computer science field. So you're the goal of IEEE, basically. They want to educate students and non-students alike on the benefits and the guidelines of networking. So they host symposiums, conferences, chapter meetings. They used to have a chapter meeting at Rockford College. I don't know if they're meeting this semester or not. I will find out. But they used to, last semester they met like once every other month at Rockford College, I think in the chapel there. And it'd be well worth your time to do it and to get involved. And they maintain a standards board. IEEE technical papers, a lot like the white papers I talked about earlier for ANSI, and you can find them online. And they're very highly respected. When they come on campus, they usually have about 200 people come, and part of them are students, part of them are, the head honchos in IEEE in this area. And they have a presentation, they have food, and they're usually covering, like last time they were covering home automation, and all the devices coming out now for home automation, and some of the careers that are out now we didn't have 5 years ago, all designed around home automation. What I mean by that is, some of you might, anybody have anything in your house that you do home automation, like your lights or your whatever through an app where you can control it? But you've heard of that, right? Or shades in the house, or your thermostat controlled with automation. That's a huge field now that's still kind of in the infancy stage, but there's jobs and markets open now that literally didn't even exist a year and a half ago. Businesses, jobs, and opening in markets because of home automation. It started in business for business automation. Now it's in homes, and a lot of people are getting into it because home users are, because it saves them money, number one. They get tax breaks for stuff for using certain things, and it's fairly efficient and fairly intuitive to use. It's not real complex for end users to use. ISO, it's an international organization for standardization. Their headquarters in Geneva, Switzerland. They're a collection of 56 countries around the world. And the goal is to establish international technological standards to facilitate global exchange in information and barrier-free trade. Widespread authority. And so if you have a third world country that's needing technology, like they don't have internet or something, and you want to pipe in internet into a village or something, these are the folks that get it done. They have the money, the resources, the technical know-how, and so a lot of times you hear of, even in our military, I had a cousin that went 4 tours in Iraq, and one of his positions was setting up Wi-Fi hotspots for kids near schools. And ISO was the folks that provided the hardware and the infrastructure for the Wi-Fi to get in those remote areas. And so that was kind of cool. So it basically set up ad hoc schools and ad hoc Wi-Fi connections for children. ITU, International Telecommunication Union. These specialize in the UN. They regulate international telecommunication, provide developing countries with technical expertise and equipment. They were founded in 1865 and they joined the UN when Israel actually became a nation again in 1947. The members from 191 countries, and the focus of ITU is global communication issues, telecommunication issues, and the worldwide internet services. And their goal is actually to provide it in third world countries at no cost to those in those countries. Because it's been proven if folks have internet and computers, even if they have a Raspberry Pi and internet, they can learn and take classes and become, better, more productive. An example was, I heard a story where a village learned irrigation through online courses on the state side online. They took some courses and built an irrigation that literally saved people's lives because it brought in fresh water. And so they were able to create that themselves. And this one of the organizations that helps bring that, along with ISO as well, talked about earlier. ISOC is an internet society founded in '92. It's a professional membership society. These folks have the technical standards for the internet. And the current ISOC concerns is rapid internet growth, keeping internet accessible for all, information security, stable addressing of internet services, and open standards. IP version 6 is what was birthed in this organization. For years we had IP version 4, which is what our networks run upon. Now if you look in your computer, even these, or here's a home, you do have two IP modes now. One is version 4 and one's version 6. Version 6 basically just gives us more IP numbers and ranges, and we'll learn more about that this semester, especially when we get into the converting IP addresses and subnetting. But basically all you need to know now is this group is concerned about all of that as far as internet growth, because they said by the year 2025, before version 6 came out, that we would run out of IP addresses for websites, because every consumer like yourself and I and business that has a website has a unique IP address, and they were predicting by 2025 become dangerously close to running out of those, and that's where the IP version 6 came in, and that was about 10 years ago when they thought of that, and it's now been rolled out. ISOC is an overseas board, specific mission. They have a twofold mission. They have the Internet Architectural Board, the IAB. It's a technical advisory group. They oversee the Internet's design and management. And Al Gore did not start that, but he teases everybody he did. IETF, the Internet Engineering Task Force. They set Internet system communication standards, particularly protocol, operation, interaction, and anyone could submit a standard and proposal. A very elaborate review, testing, and approval process for the IETF task force. IANA and ICANN. The IP, you've heard of that probably. We've talked a little bit about it already. In the video, you'll see some more about IP. But IP basically is much like your social security number. It's unique, and it has to be unique within the network you're in. It's an addressing about your computer. The IP version 4 is set up in 4 octets. Each octet has a bit, and it's made up of a byte, your IP address is. And so you've got basically 8 bits per byte, and then zeros and ones for each one of the octets. And the addressing of this is surrounded around what's called Internet Protocol. And it's relying upon central management authorities. And then the IP address management history, this actually talks about the global IP addresses for websites, okay? The first one was the IANA, the Internet Assigned Numbers Authority. These folks were the ones that kept track of, to be a crude example would be like an Excel spreadsheet, which they had hopefully better than that, but let's say they had Excel spreadsheet when they first started, or something like that, to keep track of all the IP addresses along with what businesses were assigned to that. You might have heard of a term on websites called whois. Anybody heard of whois before? If you just Google, like for instance, whois and then a domain like let's say apple.com, it'll come back with information about that web server, who owns it, contact information. These are the folks that keep track of all that. And it's legally binding. You have to put that information up there. Now, it doesn't have to go to a person, but somebody should be able to look up any website with whois and find out contact information for technical questions, legal questions, things like that. Then came 97, 3 register were in effect there. And 97 was actually the heyday kind of internet when it first really started exploding, okay? Because if you think about it, we're in 2017, and everything I read and everything that conferences that I go to, still say we're in the infancy stages when it comes to speed and what we can do with what's called the Internet of Things. And part of the Internet of Things will be what we talked about earlier, like home automation, business automation. But we're still in the infancy stages. But in 97, which wasn't too long ago, we're just talking a few years into the Internet in 97. And it was going like gangbusters. And so there was 3 folks that took care of all the Internet numbers. IANN, the American Registry for Internet Numbers, APNIC, Asia Pacific Network Information Center, and then RIPE, Réseau IP Europeans. So 3 entities in 97. Then came 90 and came into one area. Those 3 merged into one basically called the ICANN. The Internet Corporate for Assigned Numbers and Names and Numbers. It's a private nonprofit, so it is a private governmental. Actually started with a group of people. Some of the 3 I just mentioned were part of the original group, and they remain responsible for the IP addressing and domain name management. So regardless of where you buy a domain through, like GoDaddy or wherever, they submit all the information. When I mean they, like the host, like GoDaddy, submit all the information about the web owner to these folks, along with the IP address of that owner. So if you're a business and you get a Comcast or an Xfinity business plan, they generally give you 2 or 3 external IP addresses you can use. That would go to these folks. So your business name would be on it. The 3 external IP addresses, whether you use them or not, it's your business, would be on it, and they're yours. So they keep track of all that. Users and businesses obtain IP addresses from the ISP, like I mentioned. ISPs are Xfinity, Comcast, all the same now. AT&T, Verizon, just to name a few. Now we're getting to the OSI model. OSI model is basically a model to understand how things flow in a network, to put it in a nutshell. It's a theoretical model. It's not a physical anything. It's just a theory, okay? Kind of like the theory of relativity. You can't touch it or feel it. It's a theory, all right? So same thing here with the OSI model. You take the OSI model, you'll see in a second, and you look at every piece and part and function with a network, and you can plug it into one or more levels of the OSI that we'll see in a second. It was developed in the 80s from university level, created it, and divides a network into 7 layers. So physical, data link, network, transport, session, presentation, and application. It's protocol interaction, meaning it can interact with the levels above and below it, and a lot of times it does, kind of overlaps. The application layer interacts with software, but it's not software. It just interacts with software. And then physical layer works with your cabling, your NIC card, and such. Okay? So it's a theoretical representation, as I mentioned earlier, between 2 nodes and on the network. You have to have at least 2 nodes for this to work. It's hardware and software independent. Every network process is represented. It has what's called PDUs, which is protocol data units. It's a discrete amount of data, application layer function, and it flows through the different layers of the OSI, which would be 6, 5, 4, 3, 2, and 1. And it's a general model, and it's imperfect, for sure. So here's an example of what it looks like. You have 2 nodes, computer 1, computer 2, on the on the overhead there. And so we'll start with the left one there. And on the left side of that computer over here, okay, it represents coming from the NIC out, going down. And we'll say, just for argument's sake, for example's sake, it's Eagle that these computers are on, both of them, RBC Eagle. So you logged in tonight to Eagle, submitted your name, if the internet was working. You submitted your name, and it went through the application layer of the OSI model, which is Chrome or Firefox or IE, whatever web browser you were using, along with the app that RVC Eagle runs upon. That's the application layer. The presentation layer takes that data, which is your name, and begins to wrap it with correct information, like, since it's text, it's going to wrap it with text type of information. If it's video, it'd be video type of encoding. Then it takes it to the next layer, which is a session layer. The session layer will take that presentation layer, get ready to convert it, to transport it out of the network. Now we're at the network layer. And basically, the transport and session layer are used to keep the connection alive. Back in the dial-up days, when you would dial up to a connection, those of you who remember this, it would connect, do a high screech, right, and then stop, and then you were connected. That high screech was a handshaking that was going on, authenticating that your username and password was right, and then once it, found that that was the case, you were then connected with a certain speed. That's found in this presentation session layer. Transport layer and network layer, it's getting ready to package that data into whatever it needs to be, which in this case, in every case, is going to be binary, because that's what our network works upon. Goes from that to the data link layer and physical layer, and the physical layer is going to be your NIC card, your Cat5 cable. Takes that information now and goes over to the right side over here and does the exact opposite in the opposite order. Around this area here that I'm circling on the overhead, the session presentation layer, it's taking it from binary now, which it was brought from, back into digital and converting it to what format it needs to be, which in RVC Eagle, that format, when I view it on my end, is going to be text format. Okay? Everything that goes across the network is what's called encoded. Everything. It's encoded with something so the network knows what it is. It's coded with a stamp, and you'll see it in the video in just a second, so it knows what type of data it is, the size of the data, and that way, the reason for that is, by the way, so it knows when it gets to the other side, when it gets to the RVC server, that your data made it there correctly and intact. And now we're going to talk individually about one of those areas. So application layer is a top layer, no software applications, but it does interact with software. Its protocol functions are facilitating between the software itself and the lower level network that's getting ready to be pushed into. The network interprets the application's request, and the application interprets the sent data from the network. The software negotiates with the application, like formatting of the text of your name, procedure. Is there security wrappings in there? Yeah. Your security on your username, your password. That way when I see it, I know it's you and you sent it, right? Nobody else sent it. You did it. Synchronization, that deals with, again, authentication, keeping the data synced, keeping the session synced. That way it stays alive while you're submitting it. If this wasn't in play, when you typed your name in and hit submit, connection would be dead. So you have to have that and other requirements. The presentation layer, software now or application, now we're in the presentation layer. The presentation layer is a protocol, it accepts the application layer data. In this case that we're talking about is your name, your text that you submitted. It formats it into understandable to different applications and hosts. And that's where I talked about earlier, it stamps it with some type of encoding. In this case, it's a text encoding because it's text that you're submitting. If it's video, it'll be video encoding. If it's audio, it'll be audio encoding. If it's PDF, it'll be PDF encoding, so on and so forth. So an example is here is a text encoding method. Presentation layer performs coding and compression of the text that you just submitted. Granted, it's just a few characters, but to to be good to the network and to make things flow better, it compresses everything to make sure data flows faster and more efficient. Example is also presentation layer services manages data of encryption and decryption on the fly. So as it's sent out, it's encrypted. As it lands in the RVC server and I open it up, it's decrypted for me to read it on the fly. The protocol function for session layer is coordinates between the communication between two nodes. And this is where I talked about earlier, the ongoing data exchange continually, that session keeps it alive, the session layer does. And so an example is a connection between the remote client and access server. The remote client in this example we're talking about would be RVC Eagle and the RVC Eagle server. The connection between the web browser, i.e. Chrome, Fox, Internet Explorer, and the web server, which would be the RVC web server, RVC Eagle web server. The session layer also establishes and keeps alive that session and keeps it secure and determines when you log off, when you exit out of Eagle or you literally log off of Eagle. It knows that, or it can restart a transmission. Have you ever downloaded a file and it stopped? You ever had that happen before? While you're downloading it, it literally stopped. And then you go back later. Now you could have shut your laptop and it stopped, or it could have just stopped. And you go back later and you can refresh it and restart it and it continues to download right where it left off. How does it do that? It does that because of the session layer. It knows exactly what's been downloaded so far, how much has left to go, and can pick up right where it left off. Now, can you kill that download altogether and start over again? Yeah, but you don't have to. In most download servers, when you're downloading a file, it'll remember where you left off just fine, whether it's 5 minutes or 5 hours, and you can come back and continue downloading that file. And if it's a larger file, it's a good thing, right? You don't have to start all over again. But the session layer is where that takes place and where that communication takes place. It also terminates the communications. So when you log off of Eagle, you're logged off of Eagle. It's terminated. That connection's terminated. Your session's dead. It's over. You're logged out. Same thing with a bank account you've logged into. You log out, your session's over. Then brings us to the transport layer. The transport layer accepts data from the session layer. It manages end-to-end delivery. This is the one that knows the exact size of your data packet, what IP address it's going to, in this case, the RVC Eagle server. It handles all the flow control, meaning it knows all the congestion on the network and exactly what path is going to be taken. Okay? It could be slower sometimes, it could be faster sometimes. It all depends upon the network traffic and the congestion. It has built into it connection-oriented protocols and what's called checksum. What a checksum does basically is checks that the data size, packets that was sent is received 100% as it was sent. Every file has what's called a checksum piece of that file that's used in networking to know that that 10 meg file you sent me, I received that 10 meg file with no corruption or anything from start to finish. Now, it might have taken 4 or 5 restarts. It might have had to be resent 10 times. An IP packet might have dropped 20 times. Doesn't matter. When I get it, eventually it's going to be 100% because of this transport layer area, and specifically the checksum. It ensures data integrity, and in networking you have a lot of redundancy because you want to make sure your data gets to where it's supposed to go. And the network operating system, the switches, the hubs, the routers, your operating systems all work in tandem to confirm that that information's sent. Okay? So like RVC Eagle, an example would be when you hit submit and the internet died, you go back in when it's up, maybe it didn't submit it all the way, you have to submit it again, but you don't have to retype your name in, it saved that session because it's continually saving things, and that's software related, it's saving it in the software, in the database, but it couldn't push it on the network because the internet's dead, it died. So later on you can pick it up and connect again to make sure that data's sent. Transport layer also have connectionless protocols, not just connection protocols of confirming data has been sent and received. Connectionless protocols do not have to establish connection with one another before transmitting data. Make no effort to ensure data is free of error. More efficient than connection because there's no rules wrapped around it. Okay. Useful when data must be transferred quickly. Segmentation. This is a lot like, I like to draw like a cabooses on a train, segmentation. So use an example of your name. Okay, I'll say your name's Ted. Your name's Ted. It puts a letter in each caboose as it's going, it splits up your data into 3 cabooses and segments it as it goes through the network and through the wires over to the RVC server. When it comes back to the RVC server, Ted is put back together in the order it came. So we have 0, 1, 2 is the numbers of the caboose there that's been segmented. And it might be thrown out there in all different orders as it's floating around the network. But when it comes down to me, or it comes down to the RVC server, it puts it back in order using that segmentation protocol with your name in it, all intact. Segmentation breaks up large data into smaller chunks in the little cabooses of the train. It increases data efficiency and data flow. So we can take a large file and break it up into millions and millions and millions of different segments to flow across the network better. MTU stands for, in this area, in this transport layer, the maximum transmission unit. This is basically the maximum size that caboose can handle. Each caboose on the train can only handle so much data. All right, that's the MTU. The largest data unit will carry Ethernet default is 1,500 bytes is all it can carry, each unit. Its discovery routine determines the MTU, and by default, again, 1,500 is going to be the set max. You can beef that up, but you don't need to. With the speed of the networks now, you don't have to do that. Reassembly. It's a process of what I just talked about earlier on the prior slide. It reassembles those segmented cabooses back to where they were from 0 to whatever. Puts them back in the same sequence, and I can read your name, Ted, as you typed it in. It saves it, sent it, and I received it, and the data received it. So here's another visual example of segmentation and reassembly. You have a long message on the left side, goes through the transport layer protocol, segmentation, puts it in the cabooses there in the little black boxes here. A long message goes through the network, comes back, reassembles, repackages, checksums it, it's done. Now it sounds really fast, and generally it is fast, but sometimes it's not so fast, depending upon the congestion, depending upon the time of day, depending upon you have a faulty switch, you could have a faulty wire, whatever. A lot of factors can play into that. Here's a screenshot of a segmented transport layer protocol. You'll notice in the screenshot here, the TCP stands for Transport Control Protocol. It's the rules around the IP packet. All right. Now look at this. The source port always for internet on your network is going to be port 80. Port 80 is what you use to get internet connection to the outside world, and even internally, if you have a web server, that's the default port to host a web server, is port 80. The destination port, in this case, is 1958. It's a random destination port that's selected by the transport layer network in the networking. It has a beginning sequence, acknowledgement number, and a length. Then it breaks it down line by line here, same information. Then here, these flags, when I talked earlier about the dial-up, this is where the dial-up occurred. Those of you remember the dial-up modem days. Notice the different flags in here though. Congestion, urgent, acknowledgement, push, reset, synchronized, and finished. When dial-up got to the FIN, the fin, that's when the noise went away. Okay? We don't have that today. You just know when you're on the internet at home or at work, it works or it doesn't work. I mean, that's it. There's no dial-up. There is handshaking, though, that does occur, though. This handshake does occur. The synchronization does occur continually. Your internet or your NIC card is always saying, are you there? Who's there? Are you there? Who's there? Continually, all the time. Same thing with the network switches, continually. Routers, continually listening on who's connected so they know at any moment's notice when you send a file, what's the fastest route. Okay? And the fastest route might not be fast. It might just be it's going to get there the fastest. Okay? Might not be the fastest as far as speed, but it's for sure going to get there, and the data is going to flow. Next, network layer. This one is now we're getting ready to hit the physical part of the network. We're getting towards the NIC card here. So the network layer translates the network address into physical counterparts, decides how to route the data, which it already knows how to do it, by the way, and that's because of the listening all the time. So in the example of Eagle, going to the RVC Eagle web server, the RVC Eagle web server has one IP address. You guys all have separate IP addresses, okay? So it knows that IP address it's going to. It knows the MAC address of the server it's going to. And the network's switches know your IP address and your MAC address, which you'll find out what a MAC address is here in just a second. But the addressing is a system for assigning unique identification numbers on a network. Okay, so every network device from switch to hub to router is going to have a network address, as well as your network is going to have your IP address, which is your computer that's been given to you by the DHCP server. So types of addresses for nodes would be network address and logical address. Okay, network address are devices like switches, hubs. Your logical addresses are going to be what's on your computer NIC card. Okay, it can be hard-coded in, or it can be given to you by the DHCP server. In this classroom, it's DHCP server. Now, our Cisco classes that meet here, they will hard code so they can talk to the switches when they're configuring them, connecting to them. So next in the network layer is packet information, and you'll see it on the video here in a second. The packet information is those cabooses that are segmented. Each of those cabooses also have a logical address, so it notes. And it's generally going to be in sequence, that address is, okay? Routing is simply determining point A to point B, how it's going to get there. And one of the labs we do this semester is on pinging, a ping exercise. One of the pinging technologies is called tracer, where you can basically determine with one line of code, one command, how many hops it took and where data went to get to a web server. So if you're doing a tracer to google.com, you can literally see the names of the switches or routers between here and Google's web server. And generally what's cool about that is the names generally are coincided to the state that they're in, or the city that they're in, or the country that they're in. So a lot of times you'll see for names of routers in a tracer, Chai, or KC, or California, or Arizona, or Brussels, or Germany, or China. And that's kind of cool. And you'll have fun with that when we do that. But the route is determined by the internal router that's on that location, which in this case would be ours and here, to determine how that data is going to be flowed, where it's going to go to immediately. And it looks at that time what the congestion is and what the fastest route is to get there. Routing considerations that is taken into play by the router would be the priority, network congestion, quality of service, and cost of alternate routes. And switches and routers are smart enough to determine all of that. Common network layer protocol is IP, which has no rules, by the way, 0 rules. But without the IP, data wouldn't flow. Okay, it would not flow. The TCP that wraps the IP, this would be the IP here that I'm making a circle of. The TCP is the wrapper of the IP. It's the one with all of the rules, like IP address of the sender, IP address of the receiver, MAC address of the sender, MAC address of the receiver, how big the data packet is, what the checksum is, all of that. Then fragmentation, taking everything from those smaller packets and defragging them into the one packet that it came from originally. So here's an example of a network layer. You'll notice the addressing is a little different. There's the source address, the 140 number, destination address, a 10 dot number. That's a local class A, by the way, that you'll learn about this semester. The 10 dot is. The 140 be a class B, C. Actually, B in that one. And version 4 is the TCP/IP, the IP version 4, which most networks still use today, even though version 6 is available. The length of every the header is 20 bytes. The total length of the packet is 44. This here's flags, don't fragment, more fragment. Time to live, which you'll learn about in our ping lab, is 64. 64 hops before it dies in the network. And down here's a checksum, and it'll give you whether it's correct or not correct. In this case, it says it's correct, meaning it came in, everything checked off, on size, source destination. Because man-in-the-middle attacks, which we do in my 130 class, we might actually play with in this one maybe, since I'm not teaching 130 this semester. That's where you intercept, hackers will use this to intercept packets, meaning man-in-the-middle would be, we'll say this is a Starbucks in here, and I'm an attacker, I'm a hacker, and I set up a rogue access point, all right, and you guys come in, and you normally connect to a Wi-Fi access point, SSID, maybe it says AT&T or whatever, okay? I create one called AT&T as well, but it's closer to you, so when you come into the environment, you connect to mine and not the one in Starbucks, the valid one, and all data now flows through me, and I intercept it. This would actually be able to determine in some data types whether that was intercepted or not, because I would change a little bit as it's going through. So all banking, all transactions, all text, everything you do will go through my machine, and I could see everything basically that's going on because you've trusted that connection I set up. And that's called man-in-the-middle attack. A checksum wouldn't catch the file, but it could check on internet transactions on, like, say, for banking and logging into email. That's why I tell students it can happen to anybody, man-in-the-middle attack. When you're in Wi-Fi hotspots that are free and public, do not check anything secure, like banking, email, that's, personal email or whatever. Don't do that, because it could happen pretty much. You'd be surprised how easy it is it could happen. And so man-in-the-middle attack is probably one of the number one crimes when it comes to hotspots. And this network protocol here, this network layer would catch it if the hacker opened a file, made a change, and then sent it on. It would catch it then. But more likely the hackers don't do that. They just save files and then duplicate it, send it on, and then look at it later. And the reason they do it that way is they might have a man-in-the-middle attack for 10, 15 minutes, turn off the attack, and then leave, and they might have 5,000 passwords to go through. Because when a hacker connects to a computer's access or Wi-Fi, they can see all your existing SSIDs that you've been connected to. If they figure out a password that you're currently using in any one of those, they can generally hack into other things as well. Because human nature is most people use the same password for a majority of their accounts and same email. And another trick hackers use is they purposely have you fail on a login, like say a Facebook login. That's what I do for the 130. I have them all go to a fake Facebook page. They log in with a bogus username and password, and then we go to the password page to where it's incorrect. It's human nature. Within about a minute, a person will try every password that they use in a minute. Meaning the hacker now has the email you generally use for all your accounts and all the passwords you ever use within about a 5-minute hack. And so that's pretty scary. So that's why it's important to, this isn't network security, but it's networking. And so good rule of thumb, all of us have cell phones that we can tether our internet, use that to connect to your laptop or tablet. It's pretty much set up on most phones now, I think. It comes with your package. And if you don't have it, it's probably worth getting it. Because I don't think any companies actually charge that anymore. I think it comes part of it, but anyway, they might. But it's well worth sharing your phone's internet versus some public internet and getting a chance to get hacked. So data link layer is the next one. It's a function of this one is basically dividing data into packet frames, distinct frames, for the transmission physical layer we're getting ready to go into, the Ethernet. So what this is raw data, the payload, so your text that you typed into that text box, your name, that's the payload. It could be a video, it could be a data, it could be a Word document. It also has the data, which is the payload, your sender and receiver's network address, error checking, and control information. Possible partial communication mishap would be not all the information is received. So the router says, I need the IP to send it again. And that happens all the time. And you'll see that in the video where that happens, where IP packets will drop and the router will ask for it again, those IP packets. Error checking checks that the data comes in as it was sent. And possible glut of information is on purpose. So redundancy is another term for this. Redundancy is designed in networking to where the NIC gets the data without error. So two data link layers are, one is called the LLC, the logical link layer, and the other is the MAC, the media access control layer. The MAC address components, by the way, every NIC card has them, and you'll see it in just a second, has a MAC address, whether it be a phone, a desktop, laptop, tablet. It's a block ID and it's a device ID. The block ID of a MAC address is a 6-character sequence unique to the vendor. A vendor would be like 3Com, that's a popular NIC provider that creates NIC cards. Device ID will be the 6-character number added at factories, the vendor, and it's a random number that they keep track of, but unique, random and unique, both. So block ID, device ID, and it's a lot like your VIN number on your vehicle. Every car should have a separate VIN in the world, should not be the same. And same thing with NIC cards, all separate, all unique. And MAC addresses frequently depict in hexadecimal. We actually do a lab where you look at your MAC address, you determine what that is. And on your computers, you guys have at least 2 MAC addresses, sometimes 3, depending on how many NIC cards you have on your computer. So the network layer, or the data link layer, is comprised of, at the top box there, the logical link control, which is a common interface, flow control, and then that MAC address, as we just talked about. Now we're getting ready in the data link layer, as it says here, or shows up here. That's your MAC address that it's being circled right there. And that's, again, part factory name, or model name, or company name, part random unique code rendered and plugged right into the NIC card. So the physical layer, we're getting into now the NIC card where the Cat5 is plugged into. It accepts frames from the data link layer, generates signals. It does have a small voltage, by the way. And I'll mention on this slide, you can, if you're getting ready to run wires or you're getting ready to get a new computer in your basement or upstairs or whatever, and you don't want to run wires and you don't want to spend money for another Wi-Fi router, you can actually do it through your electrical on your house. They do have devices that plug in the wall of your any 2 socket, wall 110 plug-in. It plugs right into the wall, and you plug your Cat5 into the box. We'll say that's upstairs in your house, and then Down in the basement, you plug another box in a 110 plug-in, take the Cat5 and plug it into the computer, and you're connected to the network. This one up here at the top, by the way, that's got the Cat5, it's plugged into your router, your Wi-Fi router, okay, to get the internet connection. And so they're roughly start at about $70, and you get two of them, one for each location of the house that you wanted to go to. You don't have to run any wires. And it's a lot faster than Wi-Fi because you're literally running through the electrical wires of your home. And Ethernet does have a small current that runs through it. That's why we're allowed to do that. And I lived in a farmhouse when we first moved to Rockford, and I had these all over the farmhouse. And because I did not run Ethernet, and at that time, Wi-Fi routers were non-existent. So that's my only option I had. So I got this one here, or this one here. It comes about $75. I think you can actually have them cheaper now. But many students aren't aware of the fact that you can buy those devices, and it's Ethernet over electrical wire, and it's basically running your network through your electrical wires in your house. Copper transmission in your Ethernet cable. It's a copper kind of wire, and it does issue a small voltage. It's not going to shock you or knock you back, but there is some voltage that goes through it. Fiber optic, it's light pulses, and when we do the cable lab, I bring a board in here, it goes over all the different cables and all the different types of cables, one of them being fiber. And the fiber runs through glass or plastic, mainly glass, but you can run it through plastic as well, high grade plastic. And then wireless transmission, which you're familiar of, it runs through signals through electromagnetic waves. So the physical layer, data is getting ready to be pushed out. The NIC card, it's responsible for detecting and accepting signals. On the physical layer also would be your routers and switches, because it's connected to on the physical layer. Sets data transmission rate, monitors data rate errors, no error checking. Devices operate on this would be hubs, repeaters, switches. NICs operate at both a physical and data link. They kind of overlap. So again, here is the OSI layers: application, presentation, session, transport, network, data link, and physical. You have some companies, by the way, that specialize in certain one of these OSI layers. Like say, a company might say, we specialize in layer 3 of the OSI, which is establishing network connections, translating network addresses into their physical counterparts, and determining routing. Layer 3, 2, and 1, some companies also say, like Cisco would be a layer 3 for the most part, because they're dealing with all that. Network connections, translation, physical counterparts, determining routing. That's what they specialize in. But it does couple over and run into data link and also transport as well. So communication between two systems have to do with a medium of some type running through it, whether it be fiber, wireless, over electrical, and NICs on both sides. Okay, both of them have an IP addresses, MAC addresses. Both of them have unique, packaging of those through data as it's going across, being segmented, desegmented, put in the little cabooses, segmented, put back together. Then the PDUs generated the application layer. Segments are generated in the transport layer, and basically resulting in dividing into larger PDUs, a unit of data. Packets represent the data itself, having logical addressing of where it came from, where it's going. Frames generated in the data link layer has several smaller components or fields. So I'm going to continue on here. And you can see on this one here how layers do overlap some as they go across the OSI. Token ring, this is one that I think it was last week where you did the group where you had to figure out and we did a star topology on that one. But token ring was actually the very first or second, bus was first, token ring was second, networking types of protocol, how networks were laid out. And it was defined by what's called an IEEE 802.5 standard. And it relied upon nodes and ring topology. And what it did on that one is this. You had, let me draw this here. In a ring, or a token ring topology, we'll see these are 5 computers. And this computer here has the data, and it wants to send it to this computer here, which I'll circle. What's going to happen is as data flows in a token ring, it's copied onto a unit to the left and to the right, two nodes nearby as it goes across. So we'll say it's going counterclockwise. So it's going to go here, finally get to the data, and then this will be deleted, data, this will be deleted, this will be deleted once it's been received successfully. Okay. It's nearly obsolete, token ring is, but it's still around in some, older R&D, medical field. We'll still have them. Military still has them, because military and governmental stuff still has a lot of old hardware and old networks. Ethernet frames and token rings differ. They will not interact with each other, and devices cannot support more than one frame per NIC. A lot of token rings actually had 2 NIC cards, one input and one output for those to work. IEEE had an 802 project that came out. This was back after the bus and token ring was in play, and came up with the 802.3 standard, which we have today, which is with our Cat5 cable in the back there, the blue and red and white. Red generally stands for crossover, meaning you don't need a modem or switch in between to connect two computers. The blue and white usually stand for straight cable, meaning it needs an intermediate device to connect us together, like a hub or a switch. And then 802.11, you've heard of, it's the Wi-Fi standard that we use. And these are all the Wi-Fi standards in total. Even some of these here you might not have heard of, like one for like residential metropolitan Wi-Fi, like WiMAX, would be like this 802.16 broadband wireless, where it's connected in a geographical region and it's broadband over the air. And lastly, 802.22 wireless region area network, WRAN. This one basically is for the broadcast network to operate on UHF VHF frequency, which some of you might still use. I know at the house when we dropped Xfinity, we do over the air. But UHF VHF used to be, before digital over the air, was all you could do. It's all you could get with the rabbit ears. And so that falls upon the 802.22 standard. So summary, we looked at standards, ISO, OSI, the 7 layers, IEEE, and a lot of the other standards that were there. So let's do this. Now we have a fun video. I think I'm going to use so I think I took the link out of